Okay, this is section 1.5, question 13, and a student had a question about this. Basically, you have a formula, and you're plugging in all these values into the formula, which is relatively straightforward, except for the fact that your numbers start getting really big, and then your calculator does something weird. So I just wanted to show you how to work with this. After I look at this question in the book, I typically write down all of the key information, and so this is how I have it in my notebook. I copied the formula here, and I wrote down all the variables that we're plugging in, and then I put 4,500 times 216 to the third power, and I just noticed that this is inches to the fourth. But that doesn't really matter, we just use the 432. This number, because of the formula, does get an exponent. The 216 was inches. I didn't write these units down because the formula doesn't need them, but I just wanted to point out that this exponent doesn't get applied in the formula. But here, because the 216 goes in the formula, we actually do an exponent. And so I'm going to show you how I put this in my calculator. So with parentheses, exponents, we need to do this exponent before we multiply. And so I'm going to do 216 exponent 3, enter, which is already a pretty big number. I believe that is 10 million. And then we multiply by 4,500. And then your calculator gives you this, which is actually about 45 billion. That is what that number means. So let's deconstruct this. This is called scientific notation. And it's basically 4.53 times 10 to the 10th power. So 4.53, ignore the rest of the numbers for now, times 10 to the 10th power. And that's how it shows up on this calculator. If I do that same problem again here, I think I can put in the 4,500 first, times 216 exponent 3, just showing you a different calculator. And yep, that gives the same answer, 4.53 times 10 to the 10th power. So the 10 to the 10th power just means 10 times 10 times 10 times 10 times 10, 10 times. And that ends up being 10 billion, which is a 1 with 10 zeros on the back. So 10 billion, and your particular number was 4.53 times 10 billion, which is really 45.3 billion. And another way you can express this is to say 4.53 E10. This is shorthand for scientific notation. All of these are more compact ways to express a number that's too long. Your calculator is out of space and it's trying to express that number. So 4.53 times 10 to the 10th. This calculator also has this E button, an exponent button. So if I do 4.53 exponent 10, that is that same number. So this E is just times 10 to the, and then you put your exponent 10 in there. So that's how we could enter this into the calculator. And so that is the answer for the numerator of this formula, and then we need to also multiply up these numbers for the denominator. It turns out that we get this number on top and this number on bottom. And it's kind of a coincidence that they're both 10 to the 10th power. It's a lucky break because we can cancel them both out. But I wanted to show you how to put this entire thing into your calculator, because on another situation this might not be exactly the same, it might be different. So going back to this calculator here, let me show you how I punch this in. 4.532, and then this one, instead of having times 10 to the power, it's just got this little feature, the E. So I need to use the blue button, second E 10, divided by, oh, and I didn't show you how I got this number. I need to show you that. So it's 48 times 1.8 million times 432, and that's how you get the 3.73248 times 10 to the 10th. And then we want to divide these two numbers, so 4.532, and I know we dropped some decimals, there was more here, but it's going to not matter. You can take my word for that. So that, and then I do my E feature, 10, divided by 3.73248 second E 10, and that gives me the answer, which is 1.215, and then I need to look and see what are the units on this answer, but that is the correct answer. Actually, that's coming out 1.214, and that's probably because I lost accuracy somewhere along the way. Huh. Not a huge deal. It's not a big deal because I think the final answer that your book wants is rounding to 1 decimal place. So we're going to just say 1.2, so it doesn't matter that it was slightly different. So when I divide these two, I get 1.2, and then how do you know what the units are? Well, you go back to your question, and the deflection is measured in inches. So that formula spits out a number that is the number of inches. And that is not even a tape measure fraction. I think that is the answer in the back of the book. I can double check. But there's no 0.2 on a tape measure anyway. Let me just double check and make sure that is the correct answer. Yep, that's what it has in the back of the book. So decimals are okay. As you may recall, by the way, check this out. When I just did that problem, I can arrow up and arrow down, and I can retrieve that previous problem. So 1.214, I could turn this into like how many sixteenths it is, but 1.2 is fine for this one. So that 1.2 inches is the deflection of a beam. So it's just over an inch, and that just means that if you have a long beam and you put a big weight on it and you plug in the length, elasticity of the beam, could be a known entity. It would be different if this is steel versus wood versus who knows what. And moment of inertia of the beam, that one I'm a little shakier on what that means. But anyway, this is just saying that if you put a 4,500 pound weight in the middle of the beam, that this is going to deflect 1.2 inches. Okay, hope that was helpful. Let me know if you have any other questions.